Professor Alice Smith is the Joe W. Forehand Accenture Distinguished Professor of the Industrial and System Engineering Department at Auburn University, where she served as department chair from 1999 to 2011. Previously, she was on the faculty of the Department of Industrial Engineering at the University of Pittsburgh, where she joined after industrial experience with Southwestern Bell Corporation. Dr. Smith has degrees from Rice University, St. Louis University, and Missouri University of Science and Technology. She holds one US patent and several international patents, and has co-authored more than 200 papers, where she has over 13,000 citations and an H index of 47 according to Google Scholar. She won many highly cited paper awards. You may refer to her webpage. She has been a principal investigator on over 10 million of sponsored research with funding by NASA, US Department of Defense, Missile Defense Agency, and extra. She was awarded the Wellington Award in 2016 and the IIE Albert G. Horstman Distinguished Educator Award in 2012, and the Informed Warmth Award for the Advance of Women in ORMS in 2009. She is a fellow of ISE, IEEE, and a senior member of the Society of Women Engineers, and a member of Tau Beta Pi and Informs, and a registered professional engineer in Alabama and Pennsylvania. Okay, so without further ado, let me thank Professor Alice Smith, and please welcome Professor Smith. Thank you. You may try to share your screen. Yeah.
I will. Thank you very much. And I am grateful for this opportunity and for everyone tuning in, whatever time frame it is. I know in the Hong Kong area, it's late in the evening. So thank you for giving your evening up. And some of the rest of us, it's fairly early in the morning. As you can see, I used to use virtual backgrounds, but I moved just to regular backgrounds so you can see me better, because virtual sometimes messes up a little bit. So I'm going to share my screen. Hopefully you can see it.
Yes.
I'm assuming you can see this. Okay. So the talk I chose to give today is a very active research area I have right now. I'm doing a lot of work in logistics, including warehouse design and port operations and design. But my largest group right now in logistics is on drones for last mile delivery. And I got really interested in this when I was working with my colleague Chase Murray, who's now at University of Buffalo, who's a pioneer in this area, although he's quite young. And when he moved, I partnered with a newer colleague, Daniel Silva. So we've been working together along with a team of students and some visiting scholars to work on various interesting problems and questions in this area. So what I'm going to present today are two avenues of research that we've done and are continuing to do. We have others in this area, but these are the two that are most mature. And this work is partly funded by the Toyota company, and specifically the Toyota Material Handling North America, which is, it's part of Raymond, or actually they bought Raymond out, so they go by both names. Okay. And the work I'm going to present, the two main avenues. The first one is in conjunction with one of our doctoral students, Nawin, who's originally from Bangkok, Thailand. And the other is with Juan Carlos, who is actually a student down in Chile. I have a an adjunct appointment in Chile, and so I am advising him there. So let me get started. I have a lot to cover. I'm going to move fairly quickly, but of course, I think at the end we can have questions, or you can always follow up with me by email. I'd be happy to interact with you on any details or maybe some future collaborations. So there's been quite a bit done in drone delivery recently for last mile delivery. And by last mile, this means something like from a distribution center or a warehouse or some depot to the customer, to the end user. And we were particularly interested in this for medical applications. Auburn University is in Alabama, which probably most of you haven't visited, but it's a very nice state and I invite you. It's in the southeast of the US and it's actually quite rural. So there's many people living without nearby access to many things, including healthcare. Alabama is actually also one of the poorest states in the US, and particularly in the rural environment. There's many disadvantaged people. Often these are minority people. And so we really wanted to work on a problem that was interesting from a technical perspective, but also had relevance to improve the environment we live in our state. So I'm going to talk about two applications, which is the flying sidekick traveling salesman problem with pickup and delivery. That's the first one. The second is drone resupply for orders with release dates. So it's two sections. For each of these, we've also have a field testing going on. It's in a very immature stage. It was delayed quite a bit because of the pandemic, but I'll share with you what we have done on that. So we're interested in, especially in medical logistics, although the methods we've developed are general, they're not specific to medical. And as I've already said, we were particularly interested in reaching underserved rural populations in a both timely and cost-effective manner. And what we're interested in particular is delivery of medicals and testing supplies, et cetera, to the end user, to their home. And possible pickups as well, results, empties, and specimens, and so on. So this work, although we started it before the pandemic, and we think that the relevance has increased with the pandemic because there's a greater interest, of course, on testing, and seems like COVID testing is going to be with us for a long time, unfortunately. And empowering people, even in rural environments, to take control of their own health care in this way. So just really briefly on the literature, the bottom has a couple useful survey papers about drones for last mile delivery. As you can see, the first paper was in 2015. And this was my former colleague, Chase Murray, actually did this work while he was at Auburn with his student, Amanda Chu. And since then, the literature's kind of exploded. There's all sorts of variations. These are some of the more relevant works and important works to what we're going to be doing. So the first item I'm going to talk about is combining pickup and delivery using the flying sidekick traveling salesman problem. So the flying sidekick TSP, we did not term that. That was termed by Murray and Chu. Oh, I don't know why that's a Y. Okay. That's supposed to be an and. It's because it's left over from Spanish, so sorry. Anyways, so there's a truck and drone tandem for parcel delivery. The drone has limited endurance and a capacity of 1 parcel. And these are just some graphs, and they compared to just a truck only delivery. This again is last mile delivery from a depot to the end user. With using a drone, as you can see in the figure on the right, where the drone can be launched from the truck, deliver autonomously to an end user, and then return to the truck further along the route. So one of the things that we noticed about this model, and it's been a very influential model that's been improved upon and adapted by many researchers, is that the drone flies empty half the time because once it delivers the payload, it's flying empty. So we were wanting to incorporate pickup. And beyond just the fact that the drone is underutilized, pickups are extremely important. I've already talked about pickups in the medical applications where you could get empties or specimens, but just in general with last mile delivery, there's a huge amount of returns. Think about when you get something from Amazon or another online retailer, especially something I've found anyways in clothing or shoes. A lot of times it goes back. Many retailers offer free returns, and this is part of the motivation to get customers to buy their products sight unseen through remote delivery. So there's a lot of returns, and returns are expensive. It's also a hassle for customers because even though their goods are delivered to them, often to return an item, they must go to some kind of parcel service or post office. So we wanted to incorporate returns. And so obviously with a truck only, you can see we have here both pickups, which means returns, and deliveries from some depot, which is denoted with the square. And the truck can do either pickup or delivery, or in the case of the customer in the upper right, both. So here's the drone just for delivery. This, of course, is that flying sidekick problem that I've already discussed. And what we're doing is also adding pickup. Excuse me. So in this case, the drone also leaves the truck autonomously to serve customers. And the drone can either deliver or can pick up, or it can both deliver and pick up. And so this is our idea. We're the first, as far as we know, to formulate this type of model. And if you add multiple payloads, it even gets more interesting because then there's a sequence. Drones have, of course, a payload capacity and it's quite small. And so it's important if you're going to be doing multiple payloads that you do your sequence things so there's enough payload in the drone to do the pickup, which means that you often need to sequence deliveries prior to pickup. And of course, when the payload is one, this is mandatory. When it's more than one, which we've investigated, it's not mandatory, but there's still an important sequencing. So it makes the math model and solving it more complicated. So I'm not going to show you the math model. I have it, of course, but we don't really have time and it's pretty boring to go through slides of math. But this is the problem. So we're going to minimize the total completion time. You can think about it as a daily delivery plan for a set of deliveries and pickups, and we're using a truck. So one truck and one drone, Tandem. And of course, the drone has endurance issues because they fly by battery. We are going to look at the case where the drone can carry multiple payloads or multiple parcels at one time. Also, we have to be mindful that not all customers can be served by a drone. For example, in the medical supply, there may be medicines that need refrigeration or medicines that are highly regulated. In this case, the drones would not be able to handle those, and those would be needed to be delivered in person by the truck. We also include a fixed time to both load and unload the drone. And the truck we're assuming is not capacitated because it's huge compared to the drone. So these are some of the constraints. We're going to visit each customer only one time with either vehicle. Obviously, there's a flow balance equations. We've got payload constraints for the drone because of the capacity. We also have an endurance constraints for the drone. So we're assuming when the drone rendezvous with the truck, the driver will swap the battery. And so the endurance starts again once it's rendezvoused with the truck, or of course, when it comes from the depot. We're obviously going to be looking at the timing. We also, to make it more tractable, do some subtour elimination and the other ordinary constraints in the model. So these are some of the results I'm going to show you. This is still ongoing work. So here we're looking at our version of the problem, which is this long flying sidekick with pickup and delivery with multiple payloads, which is what all that stands for, versus a regular truck only, which would be a TSP, versus the flying sidekick problem that I showed you that has the drone, but there's no pickup. So I'm going to show you some results for quite small instances first of 10 customers, because we can solve that exactly. And these are the speeds and the endurances, and we're using Cplex here with the Python code. We're looking at percent return of 0, which means there's no returns. Everything's a delivery. 20% and 40%, and we're considering drone payload capacity of single, which is obviously 1, 2, and 3. So these are some results, and what these are the percent time savings of incorporating the drone with both pickup and delivery. Over in the case of the columns for the traveling salesman, that would be truck only. In the last two columns, that's the truck and drone tandem. So I think the last two columns are most important. So if you look at those, just by adding the fact that the drone can both pick up and deliver, you get significant time savings, even if the percent return is relatively low, because you've got, well, in the case of multiple payloads. But even in the case of one payload, we're getting an average of almost 7%, even just with one payload when allowing pickups. When we increase the payloads, of course, that savings becomes pretty significant. And compared to truck only, you can see the savings are very large, which gives motivation to our premise, which is that the customer, in our case, our interested customers as a rural target in healthcare, can be served much more cost effectively and more timely using this type of strategy. We also developed a heuristic. I'm not going to go through the details. This is a little flow chart, but essentially it's an insertion heuristic that loops around to try to build good paths to solve larger problems. We've got an optimality gap of a little over 5% on the smaller problems that we've tested. These are some results, again, on the 10 customer, which we can solve exactly. So when we compare it to the mixed integer linear programming solution, of course, it's very much faster. And you can see at the last column there, the percent of total service time of our heuristic over the best known, which is the one found by the MLP. It's really good. We're getting really good results for the 10 customer problem. So we're currently running larger instances with heuristic only. So some of the conclusions, this model we think can work really well for medical delivery and pickup. The time savings are significant. Obviously, payload capacity is important. So as we up the payload capacity, the model becomes more complicated and harder to solve, but you also get a lot more time savings. And remember, we're talking about medical things, which are typically small. So we're thinking that the multiple payload is actually really practical. It's not just some made up thing. I like my work to be very relevant to real life. And so this is something we're mindful of. Heuristic performs well, so it looks like it's been good. We've worked for a while to tune this heuristic. And then, of course, later this could be extended to multiple truck and drone pairs. Right now, we're doing only a single pair. Okay, so what I have now is an animation. And this was done by and is narrated by another of our doctoral students who's working in drones too, but not in these problems, Julio Jimenez. who's originally from Chile and is a student at Auburn. So what we're going to see here, and we show the Toyota and the Auburn because Toyota funded part of this. So I'm going to start the video. Okay, let me stop it. So do you guys hear the narration? I don't think you do. So let me change the share real quickly. So I need to share the sound and video clip. Okay. All right. So let me.
And delivery model. In the model, a drone and a truck are used for pickup and delivery of parcels.
Okay, I'm going to stop right there. Are you guys
Yeah, I can hear. Yeah,
you can hear the narration. Perfect.
right.
Okay, that's what I
Perfect.
thought. All right, let me start it again.
This video shows a virtual trial of an instance of the flying Sidekick with pickup and delivery model. In the model, a drone and a truck are used for pickup and delivery of parcels. In this instance, there are 10 different locations. This is how they are distributed in the virtual environment. The location of the vehicles will be indicated by 2 dots. The green dot is the truck and the orange dot is the drone.
So here the drone and the truck met. The drone delivered and the truck, it was instantaneous, but the truck resupplied the drone with battery and with more payload. So what we're seeing in the video is both truck delivery and pickups and drone delivery and pickups, of course, in the different animation windows. And of course, the drone is flying Euclidean distance between 2 points, whereas the truck must follow the roadway. So another truck drone rendezvous there. A drone pickup. And they're going to rendezvous back at the depot. This is a truck delivery. And there they are back home at the depot after a successful tandem. Okay, so
This video shows.
So that gave you a good idea on our first topic. The second is on drones for truck resupply. So this has the same type of application, but the approach we're taking is totally different. So rather than have the drones actually visit the locations of the end users or customers, we're going to use the drone to resupply the truck. And this solves a pretty challenging problem, and that is having drones interact directly with customers. And so this is kind of an issue, as you saw in the video. The drone was just dropping things off. And that can certainly work in many occasions. But if you think about some of the medical situations, you wouldn't want to just drop medicine off or tests or pick them up directly. And so you really, in some situations, do not necessarily want the drone to interact directly with the customer. And also in the environments we're targeting, the rural healthcare, some of the people might not be in a good position to interact with the drone or want to interact with the drone. And so this particular approach gets rid of all of those challenges. And instead, what we're doing is using a drone to basically go back and forth between the depot and the truck as it's out on its route to bring orders as they become available. So in the first application I showed you, all of the orders are available at the beginning of the day. But in many applications, including the medical applications, this is not true. If you think about, for example, a pharmacy application, medicines become available as they're made up in the pharmacy. They're not necessarily all available at the beginning of the day. So we're going to also take care of that by using the drone to resupply the truck as the orders become available. So the way this works is pretty simple. Again, we're assuming one depot, one truck, one drone. And so new orders will be available. And what we're going to do then is have the drone carry one or more new orders to rendezvous with the truck, and then the truck will make the delivery. So this is some of the literature review regarding this. Of course, on the right are the things about drones. We've already talked about the Murray and Chew paper. There's been hardly any work done in drone resupply. There's a couple papers you can see at the lower right. But there's been quite a bit in same-day order delivery. And those are on the left, at the top left, where this is termed in the literature release dates. In our context, it's actually release times because we're considering a single day with times, but the terminology is dates. And also there's a routing paper that's relative. So what are we doing here? We want to find a delivery route for, again, a single truck with a single drone to minimize the completion time of the entire delivery process. So the objective is exactly the same, but we're doing it in a completely different way. Again, we have the same assumptions. And here, what I'm going to show you is the first case we're considering, which is the deterministic case, which means that the times or dates in the terminology used in the literature are known in advance. So for example, if a patient or a medical office orders medicines early in the morning, they might know that that medicine will be ready at 11 a.m. And then another medicine order might be ready at 2 p.m. So these are known so that we can plan out the day. So again, we're using Cplex. In this case, the student prefers Java, so he used Java instead of Python. I'm going to show you results on instances from a landmark paper of Solomon. We've used them, as many other authors have, just to form test problems. We're using, you can see the speed. Again, the drone can fly Euclidean, the truck has to go along the road network. And you can see our flight endurance, and we're assuming the drone can carry either 4 or 8 orders. We're assuming release dates, again, this is times, are uniformly distributed between 0, which is the beginning of the day, to some number beta. So beta is our variable. And we're going to show you results for various values of beta times the TSP route. And that's just so that beta has a real, that ending time has a reasonable number. So these are some of our results. Again, I'm not showing you the math model, but it's there behind the scenes. This is a small instance of 10 customers and a drone capacity of 4. We considered betas, and you can see the betas along the x-axis of these graphs between 0.5 and 3. So as beta, if beta is 0, it means everything's available at the beginning of the day. And so as beta grows in length, then the orders are spread out during the day. And obviously it's going to take longer to complete everything because in some cases, the truck has to wait for orders to be available. So what we're comparing, the top, the darker dashed lines are a truck only, and the gray lower lines are the truck and drone tandem. And you can see in all cases, the shape of each graph is similar, but of course, in all cases, the adding the drone improves the time. On the y-axis is the total delivery time. And as the orders get more spread out over the day, the drone tends to make a bigger difference than if they're available early in the day. And these are for 4 different test problems from the Solomon test suite. So they have different characteristics in how the customers are arranged in the XY plane. This is a larger instance of 15 customers, and here we're considering drone capacities about 4 and 8, which is on the x-axis. Again, the same range of beta. And these are box and whisker plots over the different instances we ran in terms of, or different when orders would be available, savings over a truck only delivery system. And so again, these are savings, so they're bounded below by 0. And you can see it's kind of interesting as the capacity goes up, at least for these, and these are quite small instances, only 15 customers. The capacity was not really impactful in terms of saving times, because remember, also the drone wants to meet the truck as soon as possible where it's reasonable when orders become available. And you can see in all cases, again, using the drone improves upon the time. In some cases, this is a percent all the way up to a little more than 20%. So we're really excited about this approach because it's very practical in terms of it eliminates the issues of drones actually going to people's houses or the end users, both for the interaction, but also the possible complications of trying to land in an unknown or unregulated environment. So these are more controlled by having the driver deal totally with the drone. The mixed integer linear programming model gets really good gaps after a few minutes. We have developed a heuristic approach that is based on decomposition. to solve larger instances, and we're in the process of testing that. So we do have one paper out that was recently published in Computers and Operations Research, and we're going to submit another paper very soon, which describes more of our work with this. So again, I'm going to show you the animation of this particular approach.
Vehicle routing problems with drone resupply. This is an instance of the problem. There is one depot and 4 customers, all located on the same road. The box represents the depot and the circles are the customers. The release dates in minutes are written above each node. This figure depicts a feasible solution. We consider a truck speed of 1 distant unit per minute, and the drone speed is set to twice the truck speed. Additionally, we consider a deadline of 90 minutes, which means that the truck should return before that time or there will be an overtime cost. The truck leaves the depot with the orders of clients 1 and 2. During its journey, orders 3 and 4 become available. A drone departs from the depot to customer 3 carrying them. The drone arrives at the same time as the truck. After receiving the drone and unloading the new orders, the truck moves forward to customer 4 and then returns to the depot. In this situation, the extra labor cost paid to the delivery service driver corresponds to 10 minutes of overtime. If the drone is not used, the truck must wait until the last order becomes ready to dispatch. This will generate an overtime cost of 25 minutes. Alternatively, the truck could perform multiple trips, but that would be even more expensive. At the upper right-hand corner of the screen, you'll have a map showing the location of the truck and the drone. The red circle represents the truck and the yellow circle represents the drone. In the main view, you'll either see the truck or the drone's perspective. And at the bottom left corner, you'll see the perspective of the other vehicle.
So the trucks left the depot with the 2 orders that were available to deliver to them. Of course, you could do pickups here too, but we're not considering that because the truck can do pickups just as readily as deliveries. So that was the first customer. Now the truck's going to customer 3 to deliver. And the drone is dispatched from the depot carrying the orders for customers 3 and 4 because now they are available. And the drone will rendezvous with the truck near the location of customer 3, where the truck then can make the delivery to customer 3, and then the truck will move on to customer 4 to make that delivery. So this is a very obviously simple example with only 4 customers. So here they are rendezvousing, and this is customer 3, the little log cabin. We really don't live in log cabins in Alabama, by the way, but it obviously gets the rural environment idea across. So now the drone is going to return to the depot. It's done its mission for today. The item is delivered to customer 3, and then the truck is moving on to customer 4 to make the final delivery. And remember that both the deliveries to customers 3 and 4 were actually brought by the drone from the depot as they became available. For example, their medicines, the prescription became available. So here's we're at customer 4, and the delivery is made. Drone's still flying back to the depot. And then the truck would return to the depot. So that's gives you a good idea of how that would work. Oh, let's see. I shouldn't have stopped the share. Oh, there we go.
Vehicle.
Okay, So let me talk very briefly about field testing. So this is our drone. We have actually two drones. We have a smaller drone that we did early tests with, and then we invested in this Tarot drone, T-A-R-O-T, which is a leading drone company actually in the world, and they've done medical applications in Africa. If you look them up, there's some pretty amazing video of what they're doing to help rural populations in Africa with medical delivery using the drone. So we thought this was an important component. We didn't want to just be math and computation, although that's our primary aim. And so we're doing field tests, as I said, unfortunately, due to various situations in connection with the pandemic. This has been slowed down a lot, but we've done a little bit and we're continuing to do them. So just a very short video. This is, of course, is our drone. This is what it looks like. And most drones that you see for commercial use are designed to carry cameras, and they're designed to take pictures, or they're for surveillance or something like this. They're not really designed for delivery, but you can see this Tarot drone is actually a delivery drone. You can see the gray box underneath is actually suitable for payload and can drop payload. You can see the door can open, and so the payload could be dropped, or it can land and deliver payload either way. And so it's you know, a little bit, again, unusual in terms of what's available right now in the drone technology. And this thing is, so the way it flies is it's programmed. It has a flight planner. So all of the destinations and the routing is pre-programmed through the flight planner, which runs on a laptop. And so the drone flies autonomously using the flight plan. And so there's no need for an operator to manually fly the drone, though of course the drone could be manually flown. We have a web page that has more about our information. That's the link, and that's the QR code. And so we haven't published that much yet, although we've got papers coming. There we have the one paper in computers and operations research for the second application, which is the drone resupply. We also have a couple of conference papers you can see there for that same application. But hopefully in the near future, we have a couple more publications that we can share. So y'all also very nicely invited me to talk about the Informs Journal on Computing. So I'm going to have a few slides about that. I have the privilege to be the editor-in-chief of that journal since 2019. And I guess I'm going to be doing it a while. I think normally the term is 2 3-year terms, but they already extended me an extra term. So if all goes well, I guess I'll be editor-in-chief until 2026. So Informs Journal on Computing is, of course, an Informs journal. It's got quite a great heritage. It was first published in 1989. So we're looking at more than 30 years. We've published over 1,500 total papers thus far. You can see our mission statement there. Basically, what we're looking at is the intersection of both operations research and computation. And you can see our distinguished previous editors-in-chief, starting with our founding editor, Harvey Greenberg, who was a giant in the field and is recently deceased. Bruce Golden, David Kelton, Prakash Mirkandande, David Kelton again, back as an interim, John Chinnick, and David Woodruff, who preceded me. So this is our advisory board, our leadership team. We have a great managing editor. And if you submit a paper, you'll probably deal with her, Kelly, who's an Inform staff member. And these are our 6 advisory boards. Some of them are previous editors-in-chiefs, others are just very distinguished people in the field. So we have 10 areas. So if you submit a paper to Journal on Computing, you choose one of the 10 areas, and you can see what they are there. Applications in biology, medicine, and healthcare. Stochastic models and reinforcement learning. We have 2 design and analysis of algorithms, 1 continuous problems and 1 discrete. We have heuristic search, knowledge management and machine learning. We've got 1 in modeling with methods and analysis. We have network optimization. We have simulation, and then we have software tools. These are our area editors. They represent institutions from quite international and with great amount of expertise. And so we have a lot of associate editors, a bit over 70. And I did look this up before this talk. We only have 1 from Hong Kong, and he's not from your university, but we do have 1 from Hong Kong. But we have a lot of other countries represented, and we're also interested in possibly recruiting in some areas new associate editors. So there's opportunities potentially for some of you who would like to be involved. Some of the statistics, the acceptance rate varies quite a bit. The latest figures were a little over 20%, and can go up to almost a third. So you can see the acceptance rate there, depending on the year. One thing we're trying to do is reduce the time to first decision. Right now we have a median of about 130 days. So that's what, a little over 4 months for non-desk reject. So we do desk reject like every other respectable journal. There's a lot of desk rejects, and those are not included in this number. We're doing really, really well on our downloads. For the first half of this year, we have over 23,000 downloads of our papers. And our impact factor, the most recent, which was just published for 2020, increased a lot over previous years. The submissions have also steadily increased. We've been publishing more. We've got a big increase in page budget. We're a quarterly journal. I'm hoping Informs will turn us into a bi-monthly journal, which in that case will move from 4 to 6, because we are seeing a lot of activity and a lot of relevance with the Journal on Computing. So I also want to make a promo for a book that I had the pleasure to edit and to organize. This is out from Springer in their series on women in engineering and science. And it's about research of women-led investigative teams that is involved in operations research, industrial engineering, and related fields. And so there's 25 chapters, nearly 500 pages of really exciting and diverse research, along with the biographies of the women involved with this. So I strongly recommend you check it out. The research is great, but there's also inspirational stories there and great role models to improve diversity in our field. And that's the QR code and the link for this particular book. It's available as both hardbound and as an ebook. So finally, I've only been to Hong Kong once. It's been a while. This is not a great picture of me. My hair is longer, and yeah, I looked very touristic there. I was. But anyways, I was really excited to visit, and I hope I can visit your university again. And I appreciate your time. I'm going to stop the share here. And I know it was a little bit of a long seminar, but I'm more than happy to hear your comments or respond to any questions that you might have. And as I said earlier, I went through a lot of this quickly. So if you're interested in any particular aspect in more detail, please just email me and I'll be sure to respond to you. Thank you.
Yeah. Thank you, Professor Smith. So it was a very inspiring talk, and we learned a lot from your seminar. So I think we got a few questions. The first question I think is on the Q&A box. So hi, Professor Smith. Thanks for your wonderful sharing. For the first case, I wonder if the battery limit is considered. If frequent recharge may result in inefficiency of the delivery. A second question is how to control the drone. Is it automatically or manually? So from Joe Chengye from our university.
Okay, so those are both great questions. So first, the second question about the control. We're using the drone, as I showed you in the last video. The Taro drone runs through a program. So there's a pre-plan, there's a flight planner. You can think of it as an autopilot, like on airplanes. So no, the drone does not need to be manually controlled. It could be manually controlled, but that's not what we're assuming. We're assuming that the routes are pre-planned and they're programmed into the drone. So that answers that part. In terms of the drone battery life, that is our endurance constraint. So yes, we have endurance constraint. And what we're assuming is when the drone leaves the depot or when the drone leaves the truck, it's fully charged with batteries, which means that when it leaves the depot, the battery is fully charged, but also when it rendezvous with the truck, we're assuming the driver has extra batteries that are fully charged, and there's a battery swap that's done to take out the current battery pack and a brand new one, not new, but newly charged one is swapped in. So
Right.
those are both great questions. Thank you.
Yes, thank you, Professor Smith. For the others, so if you have questions, so feel free to use the Q&A box. We have the next question from Derek, also from Hong Kong Youth. So thanks for the inspiring talk. He has a question about the drone delivery. So he thinks that drone delivery is quite promising in rural areas where land is flat and there are no high buildings. Say in Hong Kong, New York City, or I think San Francisco, typo. Tall buildings are surrounded. So will drone delivery be possible in these cities? So if yes, shall the drone delivery model consider one more dimension, which is height?
Well, I think that's a great question as well. So yes, certainly in an urban environment, I think the drone delivery, the drone logistics is more problematic. I mean, from a math perspective, no, but from a pragmatics perspective, yes. And that's why we've chosen to focus more on the rural environment, because we think that's more accessible, because you do have buildings and obstructions. And of course, then if you might want to consider 3 dimensions, we are considering just 2 dimensions in the XY plane here. So you may consider a third, the Z dimension. But moreover, you are probably going to run into a lot more restrictions in where it could be flowing, because there's obviously more people, more traffic, and so on. So I think eventually drones will become a reality in urban environments, but I believe that they'll first become a reality in rural environments, that there's more low-hanging fruit, as it were, in terms of being able to save time and money, and there are fewer impediments, as you've mentioned. Thank you.
Yeah, thank you, Professor Smith. Derek has a further question. So are there more specific constraints for healthcare applications using drones? Say special equipment, stability, temperature control, and extra.
So that is a great question. So let's talk about like stability and temperature control. So I think there, as I mentioned earlier, some customers in the first application cannot be delivered by a drone. So for in that case, the order would need to stay in the truck. So maybe it's refrigerated, or maybe it's a protected item that has security. In terms of security, when we're looking at multiple payloads, which we are, this is also something we've thought about, which we believe can be solved through basically mini lockers. So the drone, let's say, has a capacity of 4. So there'd be 4 compartments, say each with medicine. And the customer, if it was a customer was dealing directly, would have a code and basically type in the code of his or her locker to receive the parcel or to load it in the case of a delivery. So I think there's definitely some technologies that are already in place to make much of this a reality, but you're absolutely right that there will be definitely situations where the drone, at least in the current technology, is not really suitable for some of the payloads.
Great. Thank you, Professor Smith. The next question is, thank you for your wonderful presentation from Maria. So she wonders if the main results are conditioned on this constraint that the speed of the truck is less than the speed of the drone, or why is this constraint important? Thank you.
Okay, so we do assume that the drone can go faster than the truck. And that's mainly reasons of traffic. So if you think about it, the drone is flying point to point at basically a constant speed is what we're assuming. Whereas the truck has to make turns. The truck needs to stop at stop signs or stop lights, or there could be traffic. And so although we assume a constant speed for the truck, we factor into that speed that there's these other just delays of driving. Okay. So, but our math model is not dependent on that. You could change the relative speeds of the truck versus the drone with no problem. And of course, as I mentioned also in the talk, the other thing we're assuming, which I think is a good assumption, is that the drone flies point to point in Euclidean space, whereas the truck must adhere to the roadways and travel along them, which takes a longer distance. So you've got 2 things operating here with the truck. You've got that the truck is in a longer pathway because of the road, it's not Euclidean distance and is moving slower overall as a mean speed.
Yeah, thank you, Professor Smith. Our next question from our PhD student, Yijia Wang. Thank you for your great presentation. So his concern is whether there are any restrictions for drones in the US, such as time, district, and flight height. Is it necessary to apply for its usage every time? If that adding constraints or applying stochastic programming should be a good way. So because in mainland China, we have such restrictions. Thank you very much.
So that's an excellent question. And that's something we got involved with in when we started our field trial. Because we had to do investigations and actually talk with government representatives to see what kind of certifications and permissions we needed. And as it turns out in the US, for the type of field trial we were doing, there is no need to get permissions. And although our student who's mainly involved with the drones became certified, so there's a certification process that's online in the US, so you can become a certified drone operator, that also was not necessary. I think in urban environments, this would be much more complicated. Auburn is located in not an urban environment. I won't call it rural, but it's not urban. And where we're flying in our field trials is not urban either. It's more like a suburban or rural environment. But certainly if flight planning had to be done each time, that would be, a considerable issue. I mean, we do the flight planning at the beginning of the day in both models. So that could be filed with whatever government authority need it to be, and then approved. And of course, if there's certain pathways that need to be avoided or certain routing that needs to happen, then those could be added as constraints. So one of our current research, which I'm not sharing because it's in a very early stage, is we're looking at disruptions. And so what about weather or other disruptions that would cause a drone either not to be able to fly or have to alter its pathway? So these things are very realistic, even in rural environments. So we're moving towards making our work more realistic and incorporating more real world concerns about the overall effectiveness and how to deal with recourse, for example, if a weather condition arose that prevented the drone from doing the deliveries it was supposed to be doing. So yeah, I mean, this isn't ready for immediate implementation, but that's kind of the nature of the beast, right, of research, is that we're trying to be forward looking, but again, very mindful of being able to actually implement this. And our partnership, which recently ended with Toyota because it was about a 15-month grant, was really good on that because they're very concerned with the implementation. I mean, their interest is in selling equipment, right? And so they want to make sure that the research that they're funding has a real world application, if not today, in the relatively near future.
Yes. So we have one question from Sadan. Thank you very much for your question. So how will your approaches, models or work adaptable with, say, Amazon's drone behave concept, which is designed to accommodate landing and takeoff of drones in densely populated areas?
So that's another good question. It's actually another line of research that we're starting to work on. We've got a number of students working on different problems where we're using the idea of kind of a remote base station, if you could say that, or beehive, where the drones would leave and return from, and how to manage that. So that work again is really early in what we're doing in terms of trying to either in one paper to locate base stations, and the other trying to look in what we're starting work on is locating base stations, but working instead of with trucks, we're looking again at urban environment where we're looking at either deliveries on foot or by bicycle. And so, you know, trying to think about how the drone could be used with some other approaches to end user delivery that are common in urban environments, especially highly congested environments that you find in major cities around the world.
Yes. Yeah. Yeah. Professor. Okay. So thank you very much, Alice. So it is a great see you even virtually. Okay. So
Okay.
from Sadan. Yeah. So I have one more question. So I think for the problem you present to us, so there are trucks and also drones, right? I think the most challenging part is the synchronization of the trucks and also the drones. I'm thinking, let's say you have the trucks, and then so there is traffic condition, right? So there may be congestion such that the travel time is stochastic. So I mean, for your model, so we assume that the travel time are deterministic. If there is
Sure.
uncertainty in the travel time, would that be, I mean, a very challenging problem that we have to consider, or is it? Yeah. So how would you suggest we solve such a problem?
So first of all, yes, we do consider our times to be deterministic. We are moving towards in the truck resupply towards considering stochastic times where the order time availability is stochastic. We're still considering the travel times to be deterministic. So let me say that the truck, so the synchronization, you're right, is really important. And a thing to remember is the truck costs a lot more than the drone because the truck is operated by a human, which is expensive, and the truck is just a bigger investment. I mean, it's a vehicle. And so you don't want the truck to wait. You don't want the drone to wait either, ideally. But the fact is they both can wait. Okay, so when they rendezvous, the drone can hover. Okay, obviously it takes battery life, but it can hover and wait, or the truck can wait. So they don't have to exactly meet every second, although our math model has that. Although some of our problems, the drone actually ends up waiting, or the truck ends up waiting just because of the sequence of routing. But we are definitely, we understand that there's differences in traffic, especially with the truck. The only paper we found that addressed that is it kind of addresses it in the way that certain windows of the day, that the route takes longer than other windows. So it's still all deterministic, but how long it takes the truck depends on when during the day the truck is going. So we are interested in moving into more of the stochastic environment. My colleague, Daniel Silva, who I've worked on, who's a graduate of Georgia Tech, and he's well-trained, and his specialty is in stochastics, which I don't deal much with stochastics. So that's hopefully going to roll out. We just haven't gotten to it yet.
Yes, thank you, Professor Smith.